Hey everyone, we're the Smoky Maps group. Our project was on fusing millimeter wave radar data and orb slam maps to enable navigation of first responders in smoky environments. Next slide, please. So first responders have a really difficult time navigating in environments with a lot of smoke. They're actually trained to basically feel their way through the rooms. Literally relying on physical touch and other bodily contact sensing, which is, as you might imagine, not very effective. Lots of injuries are resultant in this from falls from unknown ledges and stuff like that. So one really cool sensor that's come about in recent years is something called the millimeter wave radar sensor, which is a frequency modulated continuous wave radar on a chip. It has a long enough wavelength to penetrate smoke without a significant loss in returns, which is useful for mapping in such environments. Next slide, please. So one work that's been done kind of in this field of using radar for navigation in smoky environments is the work of Liu et al. And as I mentioned, it literally examines the use of millimeter wave radar as a sensor use to construct maps in smoky environments. This work uses something called a generative adversarial network, or a GAN, to generate maps, accurate maps from sparse millimeter wave radar maps in the presence of noise. What's really cool is this work also uses a separate convolutional neural net to do what they call semantic mapping. So not just telling you where the walls are, the obstacles are, but what they are, as in like glass or concrete or a door. Which is helpful as well. Next slide, please. Another piece of related work is the quintessential orb slam 2, which is one of the kind of most famous monocular slam implementations that's used quite a bit. So this method is able to track pretty aggressive camera trajectories and reconstruct 3D occupancy point clouds in near real time. So this is done. Their method uses 3 threads: one for tracking, one for local mapping, and one for loop closure. Next slide, please. So our formal problem description is we basically want to extend the work of Liu et al. That we mentioned previously. So this project investigates a way to use the generative adversarial network trained from Liu et al. In conjunction with camera data from a monocular camera to generate more robust static maps through a fusion process. We constrain the use of the system to situations where the camera has some useful visual information. Like we don't consider environments where the camera is completely saturated with smoke. Next slide, please. Yep, so this is the technology stack. We used quite a few different things, everything from ROS1 to OpenCV, NumPy, Scikit, and PyTorch. PyTorch is what we used specifically for the running inference with the GAN model we previously described. Next slide. So we actually built this radar rig by 3D printing a rig to hold the radar in place, which is the red PCB on the bottom there, in a mechanically fixtured way to the monocular camera. The benefit of doing this is that we know that wherever the camera localizes itself to using the SLAM process, that the radar is co-located because they're mechanically fixed together. Okay, so the first step in this process from a technical perspective is generating local radar occupancy grid maps. So basically the radar gets a set of returns which specify the distance to an obstacle detected in addition to its angle from the bore side of the radar. And we also get the intensity of the return. We don't use that in this specific implementation, but it is available. So from those returns, we use something called Bressingham's line drawing algorithm that basically generates the free spaces. It generates the grid locations from the radar origin to the detected locations in that return. So as you can see on the map on the bottom right here, all of the dark gray spaces are unknown, unobserved spaces in our grid map. The white spaces are free. We know they're free because nothing was hit before the obstacle that was hit. So we know that there's nothing in the way. Another note before we move on is that the resolution of every single occupancy grid map you see in this entire presentation was on the decimeter scale, so 0.1 meter by 0.1 meter. And lastly, so these local radar occupancy grid maps were kind of piecemeal put into a global occupancy grid map based on the pose of the camera radar rig obtained from the MonoSlam algorithm. Next slide, please. So as I mentioned before, the goal is obviously to build up a representation of the space you're operating in using the radar. So the global to prevent kind of a overcrowding and over densification of the map, the global occupancy grid map is only updated at certain intervals once the camera pose and rotation of the camera changes by a given threshold. And once the map is completely constructed, it's saved offline using a raw service we implemented. And then it's upsampled using the milliMap GAN model presented in the work of Liu et al. And on the right side of the slide here, you can kind of see the before and after. So the left side is our what we call our sparse point global radar point cloud occupancy grid map, and the right is the upsampled one. Next slide, please. So here's a video of kind of the global radar construction happening, global radar occupancy grid map construction happening live. So that map that's updating there, you can see is the local radar map that's basically coming in for every single return that's received. And as you can see there, the camera moved enough to justify building up the, updating the global map. And as time goes on, you'll see that it continues to fill in while still displaying the local occupancy grid map for you to visualize with. And then that happens for a little while.
So the next step in this process is to feed video images through a Monocular SLAM algorithm to obtain visual data. The pose of the system is obtained at a given time step from the localization within the map generated in this process. The map produced by the Monocular SLAM algorithm is represented as a three-dimensional point cloud, as we can see in the image. The images. So to fuse the visual data with the radar data, we have to flatten it first. And this is done by simply removing the z-axis from the 3D point cloud. But this alone generates a rather amorphic, noisy output as a result of reflective surfaces. So to alleviate this, points that don't meet a particular density threshold are eliminated, which significantly cleans up the data and gives better definition to the edges of the grid map. And each of these points is fed through the Bressingham's algorithm to build the 2D occupancy grid map and give us the empty space occupancy. So in this video, similar to that of the radar occupancy grid map, we can see it being built in real time.
So having the two maps mentioned before, we propose a method to fuse them. So first, because of the scaling, orientation, and translation issue with the OpsLAN map, we first need to find the homographic to minimize the error of these two maps. We propose we use the least square error to do that. So the error is defined as a pixel by pixel error. Once the homography is found, we then use a trust index, which is computed based on the amount of smoke. right? And then given this trust, we can have a linear combination of the radar map and the SLAM map. This will give us the new fusion map. So if the area is known in one map and is unknown on the other map, we will look at the trust index and to decide if we would like to keep this norm information based on our belief on this norm map. Next slide. For system evaluation, we did not really test the system in a real smoke environment, as it is difficult for us, and then there's a potential risk of harm. So instead, we do the following to simulate the smoke environment. First, we introduce the salt and pepper noise to the image. And then for the radar part, we drop a certain ratio of points of the radar points so that you can kind of simulate the smoke environment, the sensor feedbacks in the smoke environment. So in the bottom of the slides, you can see the original and original ops lamp and radar points, and then the noisy ops lamp and radar points respectively. Next slide. So having the original maps and the noisy maps, we now can fuse those maps using the proposed method. So for evaluation, we use the same pixel by pixel error matrix defined before to compare our results to the ground truth map. Next slide. So by comparing this error index, we have some results. First, the upsampled radar map has a less error index in comparison to the original sparse radar map. And then the fusion result we have also has a even less error in comparison to the upsampled radar, and of course the OpsLAM result. And then these two statements hold true over each of the noise levels, which means that our system is working in non-smoke environment and also in smoky environment. Next slide. So there are still some problems in the current method, and there could be some improvements. First, the odometry now is estimated from the OpsLAN. In the future, we can use additional sensors to do that, like the IMUs. Second, the radar sampling method now is running offline because the upsampling method is using Python 3, but the ROS version we have right now is Python 2. A potential solution is to do it in ROS 2, or we can upgrade the system to Python 3 compatible ROS. The third one is that the OpsLAM point count needs to be, the scaling factor of the OpsLAM point count needs to be adjusted manually right now. In the future, we like to do it, we like to choose these scaling factors automatically. Yeah, next slide. The rest will be the references. Thanks for watching.